EBSCOR, the experimental program to stimulate competitive research, is a National Science Foundation grant program. The goal of EBSCOR is to strengthen science and engineering research and education throughout the United States, and to enable states like Wyoming to be nationally competitive in these areas. EBSCOR aims to improve scientific infrastructure in Wyoming and build science, technology, engineering, and math research capacity across the state. One way Wyoming EBSCOR helps strengthen science research and education is through student programs such as the Summer Research Apprentice Program, also known as SRAP. SRAP is an intensive 6-week paid research experience for high school sophomores, juniors, and seniors aiming to attend college. It offers students a hands-on research opportunity in science labs across the University of Wyoming campus. Students work one-on-one with a faculty mentor throughout their time in the program. SRAP not only provides students with a paid internship and real research experience, but also helps prepare them for college life.
Our last set of presenters, Miss Elena Martinez from Denver, Colorado, and Mr. Holden Bindl from Fort Bridger, Wyoming. Together they will be doing their presentation on time-resolved decay of carrier electrons in quantum dots.
Hello, my name is Holden Bindl.
And I'm Elena Martinez.
We did research with John McCall on decay of excited electrons in quantum dots. And it was time resolved. Our field fall under electrical engineering. What we were basically doing is we were looking at the solar cell. The world is falling into an energy crisis, and we're starting to run out of our fossil fuels, so we're having to turn to renewable energy resources. And one of those is solar cells. We're going to be using quantum dots in our experiments. Quantum dots are nanoparticles that are made out of cadmium selenide and are semiconductors just like silicon.
We're also using nanowires, which are made out of zinc, tin oxide, or zinc oxide.
The electron and the excited electron hole pair. Electrons can be excited two ways, thermally and by photon absorption. When an electron gets excited, it is able to leave the nucleus of the atom, and this creates a hole. The hole is basically an empty state where the electron should be. This causes the electron to move into what is called the valence band, and the hole moves into what is called the conduction band.
So our quantum dots and our nanowires put together are considered semiconductors. Semiconductors are materials that are in between a conductor and an insulator, and it has a crystalline structure. So one way we research these quantum dots and nanowires is through photoluminescence, which is how long an electron can be excited.
This here shows the electron being excited and moving into the conduction band while the hole moves into the valence band. When we look at this, we get two different forces. We get the force of diffusion, which is where the hole and the electrons want to mix together, that way there's an equal amount in the same space. And then there's also the force of drift, which is where the electron wants to move to the hole. These two forces are equal, and so it keeps them from moving, but until we apply some type of force, then one of the forces will become stronger than the other, and we'll be able to move an electron or a hole.
Okay, so like I said, photoluminescence is one of the methods we use, and we excited the electron through the laser, and we see how long the electron can stay excited in its high energy state.
We also measure transient absorption. Transient absorption experiments are done using a pump and a probe beam. The pump excites the electrons, and the probe will measure the amount of excited electrons. Our objective is to find the decay rate of carrier electrons in quantum dots. We're going to use two different methods: differential transmission by means of transient absorption, and light emission measurements based off photoluminescence. This right here is the setup for a transient absorption experiment. Right here we have the pulse beam and a probe beam. The probe is going to be slightly weaker than the pump for certain reasons. The pump is going to go through a delay stage and then be chopped into sections. When the pump goes through the sample, which is right here, it'll excite the electrons inside the sample. The probe is then sent through the sample, and then the differential transmission rate will tell us how many unexcited electrons there were, because the probe would come through weaker. If all the electrons inside the sample were excited, then we would have a 100% efficient sample right there.
Okay, so the next method is photoluminescence, and we did this with this structure. So we have the OPA, right there, and so we shine a laser through that to lower the wavelength. Then once we get through that, we shine it through a couple lenses to direct it to the monochrommeter, which the monochrommeter spreads out the wavelength so we can detect a certain wavelength. Then it goes through the detector, which detects how much light is given off the sample. Then it goes through a digital lock-in. We needed the digital lock-in because computers don't use the electrical data, or they don't use electricity data. So and it only takes digital. So we needed to convert it and then send it to the computer.
The decay rate of carrier electrons is one of the things we can get from absorption, and this will always be time resolved. Data from absorption experiments allows us to see the light properties of materials, and we can also determine the light energy efficiency of a material based off of photoluminescence and transient absorption.
So we're not studying the whole solar cell, we're just studying parts of it to improve it.
This is a transient absorption experiment, and these are the results we get. As we can see here, the fully excited state is 26 based off the differential transmission. That means that it gets excited very fast, according to if you were to compare this to a normal silicon solar cell. And as we come down here to 50 picoseconds, we can see that it's starting to relax, and it's at 20. This relaxation is actually very fast compared to a silicon. Normally a silicon would be at 50 differential transmission at 50 picoseconds. So this is not very efficient at all, according to differential transmission. And it was excited at 540 nanometers.
Okay, so these are the graphs for photoluminescence. This is the photoluminescence intensity dependent, and then this one is the doped zinc. So this peak is at 480, and this one's at 383 nanometers.
What doping does is doping allows us to make the cell more efficient. It gives us two different types of semiconductors. What basically doping is doping is either removing or adding an electron to the semiconductor so that it either becomes p-type or n-type. That means it has an extra electron or it has an extra hole.
So for photoluminescence, we use a method called doping, and we doped our material to 5%, and the sample absorbed the light, which we created a whole pair once it went up to the convection path. And what we were trying to do is keep the electron separated from the whole pair to keep the energy that we have, that the electron took from the light.
We want to keep the recombination time slow. That way we're able to conduct it faster away from the semiconductor. So it becomes more efficient. Because if they recombine too fast, then we won't be able to get them out of the electrical circuit.
So like I said, we weren't examining the whole cell, we were just examining some parts to improve the efficiency. So the information given can help us improve on the solar cell.
Different things to look at might include nanowires and more doping, because we're trying to find a way to make this as efficient as we can so it can beat silicon or even come equal to silicon solar cells. We're trying to do this because silicon requires a lot of heat and pressure in order to form it into an actual solar cell. But with quantum dots, it's just adding two chemicals together. So we'd be able to create it cheaply and inexpensively, and it can even come in a paint-on solution. So you can just paint it on your roof and use it.
So here's our references and our acknowledgement.
We'd like to thank EPSCoR and NSF.
And then John Caller, professor by Chavi, my grad student.
Meg, the postdoc, and SRAP and the University of Wyoming. Are there any questions?